Often we want to know the concentration of a reactant that would remain after some specified time, or how long it would take for some amount of the reactants to be used up. But how do we do that exactly?
Hold up.
Hello everyone, my name is Blaise and I'm here today with Lewis. We are going to show you how to answer the question in the intro. How do we get the concentration of a reactant that decreases in a reaction after a specified time? In chemistry, there are many formulas and equations to solve for exactly that. But today, we tackle only the three most commonly used formulas, which are for the zeroth, first, and second overall reactions. For a hypothetical reaction, which is A dissociating into products, that is in zero order, the reaction rate is independent of concentrations. We can write the rate law expression for this order as A equals A naught minus AKT. A naught is the initial concentration of A. A is the concentration left after some time, which is T, and small letter a is the coefficient of A in the equation. Because rate is always in the units of molars per second, the units of K, the rate constant, is molars per second because the concentrations do not have units since they are raised to the power of 0. Now the half-life of a chemical means the time it takes for the amount of the chemical to decrease by half. To put this into perspective, it's basically like how long does it take for you to drink half a glass of water. But instead of you drinking, the water just decays. And it's not limited to water, it could be any chemical. In equations, it just means that A becomes A naught over 2, which is half of the original amount of chemical A. We signify half-life as T sub 1/2 and substitute A in the equation for A naught over 2. And then we equate T sub 1/2 until we finally get to this formula for the half-life of a reactant in a zero-order reaction. Now let's have an example for the integrated rate equation for the zero order. Let's use the example reaction a while ago to have again as an example, but instead of products we will have B plus C, and for A's coefficient let's have 2. Now our initial concentration of A is 2.5 molars, and the rate constant is 0.05 molars per second. What will be the concentration of A after 12.5 seconds? Let's plug in our values in the formula, and we get 1.375 molars. Easy, right? Well, what is the half-life of the reaction? Again, we just plug in values into the formula, and we get 13.888888888888, and so on, or 13.89 seconds. After the zero order, we now get to the first order. We write the rate law expression for this order as ln A naught minus ln A equals AKT. K now in this equation would have units of just per second, not molars per second, because the concentration of the reactants would have the molar units, since they are now raised to the power of 1 in the first order. Changing the units of K just means that we are maintaining the units of the rate of the reaction while changing the units of the concentrations. Now again, substituting T sub 1/2 for T in the given equation, we can get the formula for the half-life of a reaction in the first order, which would be T sub 1/2 equals ln2 all over AK. Now let's have an example for the first order. Let's use the previous hypothetical reaction, A dissociating into B plus C. For A's coefficient, we have 2. Now our A naught, or initial concentration, is still 2.5 molars, and the rate constant is 0.05 per second. What will be the concentration of A after 12.5 seconds? It's just a matter of plugging in values at this point. After doing so, we'd get 0.812 molars. Then, for finding the half-life of the reaction, we just have to plug in the values as well. You'd get 7.702 seconds after doing so. That's about it for the first order. Let's now move on to the second order. We write the rate law expression for this order as 1 over A minus 1 over A naught equals AKT. K in this equation would have units of per molar second, not molars per second or just per second, because the concentration of the reactants would have the squared molar units, since they are now raised to 2 in the second order. The units of K must change in order to keep the units of the rate of the reaction at molars per second. Now, again, substituting T sub 1/2 for T in the given equation, we can get the formula for the half-life of a reaction in the second order, which would be T sub 1/2 equals 1 over A naught times AK. Now let's again have a problem. Let's use the previous hypothetical reaction A dissociating into B plus C. For A's coefficient, we have 2. Now our A naught, or initial concentration, is still 2.5 molars, and the rate constant is 0.045 molars per second. What will be the concentration of A after 12.5 seconds? It's again a matter of plugging in values, and after doing so, we'd get 0.656 molars. Then, for finding the half-life of the reaction, we just have to plug in the values as well. You'd get 4.444 seconds after doing so. We are now finished with the common integrated rate equations. Let's have a quick look at a table which sums up the equations and units of K per order. The integrated rate equation for zero order is A naught minus A equals AKT. For the first order, it's ln A naught minus ln A equals AKT. For the second order, it's 1 over A minus 1 over A naught equals AKT. The half-life equation for the zero order is T sub 1/2 equals A naught over 2AK. For the first order, it's T sub 1/2 equals ln 2 over AK. For the second order, it's T sub 1/2 equals 1 over A naught times AK. The units of K in the zero order is molars per second. The units of K in the first order is per second, and the units of K in the second order is per molar second. Thank you for watching. Please leave a like, a comment, and subscribe for more videos.